Okay, so I think let's move back with one more example, and we'll try to see that if we need to design our own custom hardware for application, how do we do it? So the application which we did for image processing, that was at much higher level of abstraction. So let's get into little more detail. Okay, so in this part, what I would like to design is I would like to design an hardware that will compute GCD. What is GCD? GCD is greatest common divisor. It is also called HCF, highest common factor. So HCF or GCD, how do we compute that? We'll see. So the problem definition says that there are two numbers x and y, both are 16-bit wide, and a computation will start whenever assert signal will arrive, and it is asserted high. So till a start signal is asserted high, you will keep on computing, and then computation will go on till your output Z is written, and there is another signal EOC, end of computation. EOC is asserted. So this is the plain specification, and we also let's say this is the overall block diagram. That means that input is x and y, both are 16-bit wide. Output is Z, that is also 16-bit wide. There is a start, there is a EOC, and we also assume that it's a synchronous circuit, so there would be a clock here. Okay, so now, what about the algorithm? Let's keep this algorithm. One of the algorithm to compute GCD. Here, what we say is that till start is equal to 1, we keep on waiting. So that means the algorithm will not start unless start is equal to 1. So when start is equal to 1, then what we'll do is first we'll take x and y as a input, and we'll also assign end of computation equal to 0. And then this loop will iterate till x is not equal to y. We will keep on computing, and if x is not equal to y, so that means either x is more than y or either x is less than y. So if it is x is more than y, then we will simply subtract x equal to x minus y. If y is more, then we will say y equal to y minus x. Okay. Yeah, so I should have written here, y, and then we again keep on going for this loop. So whatever is the larger one, a smaller number would be subtracted from the larger number, and this loop will continue till x will be equal to y. So when this loop will finish, we will say that either x or y, they are equal to Z. We'll also assert our end of computation signal, and we'll send go to S, means we can wait for the another start signal. Now this algorithm is one of the example that if we have to do for any application, how can we go ahead and design it in a systematic manner, so we can define some steps, what steps to be taken, and then we can follow those steps. Okay, so and also this particular example will try to suggest that even if the applications is bigger, then how can we can go for it. So if I need to design a hardware for computing the GCD, the steps which I'll follow is, first thing I'll do is I'll identify how many resources are required or how many resources I can provide. So both of these two things are slightly different. So based on the application, so for example, in a context switch. So in the image processing application, which we have seen in our previous part of the session, we see that it could be like based on the number of multipliers, number of adders, the steps would be different. So although the requirement says there are 9 multiplication required to design one pixel processor, although if the number of multipliers given are not 9 but 5 or 6, then the algorithm need to be, hardware would be slightly different, it can still be done. So what are the resources required? What do we mean by resources here? Resources would mean essentially what would be the number of registers, what are the number of registers, what function units, what operations are performed. For example, addition, multiplication, in that case, carry, save, adder. So all those, what are the hardware function unit that would help me in doing this task. So identifying resources, identifying how many resources is the first step by looking at the application. Okay, and after doing that, then we connect these resources in form of a data path. We see that what is the flow of path, how data would flow through these resources. So this data path designing is also the next important step. And once data path has been designed, then we will identify the control path requirements, and we'll identify which all signals would be required from the control path, and then we'll design the state machines, implement that state machine, and then the circuit would be complete. Okay, so one more thing to do all of these things, to do all of these steps, we also need to break our algorithm into smaller computational parts. So sometime these steps, for example, you're writing in the C statement as one big statement which could be broken into multiple pieces. For example, you want to access a 2-dimensional array or a 3-dimensional array. So just to identify where that element of 3-dimensional array exists, you need to do index computation. So that itself could be a multiple sub operations. So finding all these sub operations is also important. And to define these state machines, we also need to identify that how many operations can be done in a single cycle. So there could be some time that all of these things looks independent, but because some operations would take more like number of cycles. Okay, so let's try to do with this GCD algorithm and see how it goes. So first thing is finding the number of operations. Yeah, first step is finding the resources. So resources, how many resources do I require? Let's first talk about the operations. Operations, one operation is this comparison operation, which says that x is not equal to y. So I'm comparing x with y and finding out whether it is equal to or not equal to. And there's another comparison operator which is used here, which says that whether x is less than y or x is more than y. So this is one operation. The other operation I require here is the subtraction operation. So as far as function units are concerned, I would say here are only two function units. One is comparison, other is subtraction. So now only one of these subtraction would take place, either this subtraction or this subtraction. So I can say I would require only one subtraction unit. Here we can say this comparison and this comparison. So both of them can be done in a different cycles, would require different cycles, or even if because they would be done in a different cycle, so we would require only one comparator. Now to store the intermediate values, we would also require at least 3 registers, one for x, another for y, one for z, and also 1 bit register would be required for end of computation. So these are the resources, and plus to connect all of these things, we would also require some multiplexers, etc. So given enumerating all the resources, then the second step would be we'll draw the data path. We'll see that how that computation can be done and how all the relevant inputs can be sent to those relevant function units. So this we have done. Yeah. So yeah, let's say if I would like to do, then you see that I would require these register R1 and R2. R1 would store the values from X, and this R1 will also store the values from the output of my subtraction. So output of my subtractor will also go back to be given as the input to mux, and similarly R2 also. So R2 will receive either from Y, or as the output of subtraction it can receive the input. Okay, so the next thing is we also require comparison. This comparison will always be done using x1 and y1, so basically r1 and r2. So it doesn't require any mux. But subtraction, sometime you would be subtracting r1 minus r2, sometime r2 minus r1 based on the comparator output. So that's why we would require a mux here. And when computation is done, the value of R1 would be copied to R3. So there is again no mux required here. So end of computation would be possibly generated by whenever my state machine is done. So this is my data path. This is how my data would start, and I would demarcate this as the data path. Now the second would be what all control signals would be required. So control signals are required, for example, to manage this mux, that which input to be taken, either X or the output of subtractor. So let me add all these control signals. So I would require select R1 to select whether to select from X or whether to select from subtractor. Similarly, I would also require select R2, and I would require load R1, I would require load R2. So when load R1 is there, then only the values in register R1 would be loaded from the previous values of X or subtraction. Okay, so similarly here also for these two muxes also we would require either select op1 and select op2, and comparator would generate these two results, equal and greater than. So this equal to and greater would be the input to my my control unit. So and this R3 would also require load R3 as a input signal, and EOC would require two input signals. One clear EOC, that means in the starting, whenever we start, we'll make this EOC end of computation equal to 0, and whenever my computation is done, then we'll use this preset EOC. Okay, so all of these signals would be generated by our state machine, and this has to be consumed by the data path. So one thing to be noted here, that first of all we need to design a state machine which would control all the accesses, which would control all the steps, that when comparator or subtractor or addition or subtraction or these muxes or these registers to be loaded, and when the computation has to take place. So this state machine is deciding that flow, plus also it is generating all of these variables, suitable variables. So then I can go for the state machine. The state machine, there could be multiple ways to design the state machine. So let's say this one is one of the instances. So S0 state signifies that we are still in the starting phase. We are waiting for the start signal. So if start is equal to 0, then we'll keep ourselves rotating inside the S0 state. Whenever start is 1, then we'll go to S1 state, and we'll stay there in S1 state for 1 cycle, and we'll go to S2 state. So S1 state is essentially to load the registers correct, and then S2 state we will compare with the equal. So if it is equal to, if R1 is equal to R2, then we will say that we are done. And if it is not equal, that means we have to go to S3 state. In S3 state, we will do comparison. So based on if it is greater than, it will go to S4 state. If it is not greater than, it will go to S5 state. And after one cycle, again, it will check whether both of these values R1 and R2, they're equal or not. Okay, so this is the overall 7 states, and we can also define what kind of operations. These are the data flow operations, and these are the control flow operations, which are happening in each of the states. So if it is S0 state, then control operations is essentially resetting all the variables, all the signals, and if it is S1 state, we are copying X into R1, copying Y into R2, and also assigning EOC equal to 0. And the control signals of load R1, load R2, select R1, select R2 need to be generated accordingly. And in S2 state, we are comparing R1 and R2. In S3, also we are comparing R1 and R2. And based on the results, we will compute this S4, S5, and S6. So if it is equal, if it is greater than, we'll go to S4 state. If it is less than, we'll go to S5 state. Or so, and accordingly, we'll also select this select op operations. And the last state is S6, where we'll assign R1 equal to R3. So this is how the operations in each of the state can be decided, and accordingly the control can be decided, and then we can implement the whole algorithm. So one more thing before we go into demo, need to be explained here is that you see, we have divided our whole circuit into two different parts. One is data flow, or the other is the control path, the data path and control path. So as we discussed yesterday, data path would be important to determine what would be the latencies or what would be the clock cycle, while the control path will determine in what state, in what particular clock cycle, the circuit will be in which particular circuit would be doing what task. Okay, so now when we design an RTL, so this particular design is also called a register transfer level design, because we know that in what cycle we are performing which operations. Okay, so when we are implementing this RTL, so there's various ways of doing it. The way I am doing it is in a more idealistic way, where the data path is actually represented using data flow, and where control path is represented using behavior. Okay, with that, let us go back to our demo. So maybe what we can do is we can keep this in front of us. Sorry. Yeah. Remove this. We'll remove this. Keep this here. Okay, so you will see the input output of the module is very similar to the way we have defined our input is X, Y start, and EOC and Z are the outputs. We also define X and Y as input, and Z is a wire. We are not defining it as a register here. Okay, so because R3 is a register. Now these are R1, R2, R3 are defined as a register, and these are various declarations, and we also define all these 7 states here like enum as we did yesterday. These are the various signals which we are writing here: select R1, select R2, load R1, load R2, select F1. So all of these has to be defined initially. Now the data path part. So in the data path, there are 3 registers. So I'm using this always at the rate clock so that these are implemented like a register, and based on the selection value, based on the load R1 value, the correct thing will go and will be stored in these registers. Okay, so this is how we will model register R1, register R2, and register R3. And now the rest of the data path. So this mux and comparator. So you will see that when R1 and R2 both are equal, so then we will generate this equal signal. And when R1 is more than R2, then we will generate this greater than GT signal. Similarly, the subtraction part. So there are 2 things. One, we have to implement this mux. So the mux are implemented by saying that if select op1 is 1, then we will say R1 should be equal to op1. If select op2, select op1 is 0, then R2 would be equal to op1. Similarly here also, op1 and op2 both of them are calculated, and then subtract result is generated. So you will see op1, op2, sub result, all of these things are wires, and then they are being generated. Now EOC is also designed like a register, so that's why there is a @ always postage clock, and we decided if it is clear EOC, then EOC is assigned as 0. If it is preset EOC, then we are assigning EOCT as 1. Okay, so and then control path. In control path, this is the state machine as we have done it yesterday. So this S0 state is essentially our, so if this S0 state is our initial state. If my start is 0, I'll keep assigning my state as S0. If start is not equal to 0, means start is 1, then we are creating the switch case where we will change the state. If start is there, then S0 would be moved to S1, and S1 will always be moved to S2. So it will consume 1 step, and then we will move to S2. So during this S1, we'll read our registers R1 and R2. So and then in S2, we will see if it is equal, then we will make our state change to S6. If it is not equal, then we'll change our state to S3. And in S3, based on greater than, we'll change state to S5 and S6, so on and so forth. So all of these state machines are generated like this, and then there's some signals need to be generated. So these signals are generated separately, so because they would depend on the state. So as soon as state will change, so we will also generate all the signals, whichever is required in which state. So when we are designing like this, we have to draw a diagram like this, and we also need to correlate our hardware, our Verilog model in correspondence to this particular level. So now I can, just a minute. Okay, so similar to that, now we can do our test bench also. In the test bench, we will we will assign some test values so that so that we can see whether it is correct or not, and then we can dump files. So yeah, this is the way we can write our test bench. There is yeah, so with this I would like to close. So there is some problem with the simulation, so somehow it is not working at this moment. So as I will share the code with you, then you can see that yeah, so then it would be, you can try it yourself when the code would be shared with you. So with this, I'll go back to our presentation, and then yeah, we are done for the day. And then if you have any questions, then please ask.